Okay, so let's start today's session. Yeah. So, good afternoon, people who have joined. Uh, as you all know, this is in the sessions for NPTEL course Solid State Physics. Course instructor is Professor Amal Kumar Das from IIT Kharagpur, and I am Rinalini, PMRF Research Scholar from School of Physics, University of Hyderabad. People, if new, so we have these sessions every Saturday from 3 to 5 where we discuss if any concepts needs clarification or something, whatever has been taught in that week lectures, and also we mainly focus on solving related assignment problems so that you guys can get guidance for solving your assignment problems. So this is the fourth week, and let's have. I don't know why it comes. I have changed this to 1, 2, 3, 4. I don't know why it still shows up like this. Let me see. Eh, it's okay. So last week we had discussed how to calculate interplanar distance between parallel planes, and we had got this formula here that if we have HKL plane, there is some HKL plane where the intercepts are on the x-axis, the intercept is A by H, on y-axis it's B by K, and on z-axis it's C by L. When these are the intercepts on x, y, and z-axis, these are the intercepts. Then for this HKL plane, the distance between these parallel HKL planes will be, we had derived and we saw that the formula will be h by a square plus k by b square plus L by c square. This is over 1 over root. Okay. And if we know that this crystal system that we are talking about, it's a cubic system, that means A is equal to B is equal to C, then this formula simplifies to A over under root h square plus k square plus L square. Just to make it clear, even this formula that we found out here, if you remember in the derivation, we have assumed that all these angles are 90 degree, because if they are not 90 degree, then the formula becomes a little complicated, because we have to consider all the different alpha, beta, gammas angle between these axes. But here we are taking for orthogonal system where all these angles are 90 degree, and especially when we consider the system is cubic, that all the three sides are equal, then the interpolation distance will simplify to this formula. So this is what we had discussed last time, and also we had discussed that like we understood we how we get to plane. We check its intercept, then take reciprocal, simplify it to the smallest integer, and put it in these parentheses. Then that becomes our HKL plane. Someone's mic is on. If you have question, you can ask. Otherwise, please mute it. This is HKL plane, and then when we talk about family of planes, because we were saying right that if this is say 100 plane, then there in parallel we will have one more. In parallel we will have one more. So to show that family of planes, someone's mic is on. Can you hear? Nana, your mic is. Yeah. Okay, thank you. Yeah. So yeah, when we want to represent family of planes, like if for here this case 100, this denotes single 100 plane, but when we have this or maybe 100 is similar to 010 because the same atoms are occupied. We had discussed these things, I'm just revising it. So these all also can be part of same family. In that case we represent it by this.
Hello,
Hello,
madam.
madam,
You are
you are
not
not
audible.
audible. Oh,
Hello,
hello,
madam. You are
madam, you are
not
not
audible.
audible. Sorry, should I start again? I'm sorry. Wait.
You can continue. You can continue.
Yeah, but maybe I'll just. Okay, anyway, yeah, we had not started much, but it's okay. So I was just. Thank you for telling. I was just revising what we had discussed last time. That we had discussed how we get the formula for interplanar spacing between the planes, and then how we represent the plane and then family of plane. We write the oops. We write the index, and then when we put it in these brackets which are called braces, then this means that we are talking about that family of planes. And then directions, when we talk about directions, we put them in these kind of brackets. And when we talk about family of directions, again, like if direction is say some 100 direction, and then I put another parallel to it, then that will be family of plane because the direction is same. So it will be the bracket I will use is this. So these were things we had discussed last time. And after this, yeah, the next thing was, I'll just give you the formula. The next thing was, if we have two different planes, if we have two different planes, then what, like how to calculate the angle between them. So we had derived the formula, and the formula comes out to be this: cos theta is equal to h prime, where this hkl is for one plane and h prime k prime l prime is for another plane. So yeah, so the formula is h prime a square plus k prime b square plus l prime c square. In the denominator we have h over a square plus k over b square plus l over c square, and then all the parameters for the next plane: h prime by a square plus k prime by b square plus l prime by c square. This also, this is all in denominator. So this was the formula for finding out the angle between two different planes. Okay, so this we had discussed, and then we had also discussed further uh, crystal symmetry. We had discussed about type of symmetries that we see around us: rotational, mirror-like, reflection, inversion. And then in crystal or unit cell, how we identify these type of symmetries that we had discussed, that we have identity, reflection, rotation, inversion symmetries. So now next, when we have already understood these symmetries and planes, so this in this week a very important experimental technique was discussed, which we call X-ray diffraction. So the whole week's lecture was based on this experimental technique called X-ray diffraction. It's a very important kind of experimental tool that experimental people use in physics or chemistry lab when they want to find out what kind of element or material they are working with. So we'll talk here. We'll talk about how it works and what information it gives, and then how it's produced also. So X-ray is a kind of electromagnetic wave where, like other electromagnetic waves, it has particular wavelength and frequency associated with it, and it's of course not in visible light range, otherwise we would have been able to see. So visible light, which is around 400 to 700 nanometer wavelength, X-ray has very small wavelength, which is like 0.1 to 1 nanometer. And just to recall, 1 nanometer means 10 to the power minus 9 meters. So it's very, very small. Then, I mean, it's a very small quantity, but still its wavelength is, it's also associated with color, that it's out of the visible light range, so we don't see it. And this is, its wavelength is very important because of this particular range of wavelength, we use it for investigating our materials. And why so? Okay, so X-ray, as I told you, its wavelength range is about 0.1 to 1 nanometer in angstrom. Usually we always write X-ray diffraction related wavelength, we put it in angstrom. So in angstrom it will be 1 angstrom and 10 angstrom, because the relation is 1 nanometer is 10 angstrom. It's smaller unit than nanometer. And 1 angstrom, just to make it clear, is 10 to the power minus 10 meters. So it's 10 times smaller than 1 meter. So why we choose X-rays for investigating atomic, to know what kind of atom, not what kind of atom, but what kind of unit cell structure we have. Like we were discussing in the beginning, that we have atoms arranged in our material, right? We were talking about single crystal, or when we were even talking about solids, liquid and gases, we were discussing that in solids we have all of them together, in liquids they are moving a lot here and there. So X-ray we are not able to use for liquid and gaseous because they don't have any pattern regularity in them, right? So only for solids we are discussing. But even in solids, we discussed we have crystalline materials where the atoms are arranged in some kind of order. Okay, and then we had amorphous, where the atoms are randomly arranged. There is no order. In crystalline also, we have single crystal, something like this, which is like throughout the material, the same pattern is can be observed. And the other was polycrystal, where we see that there is some ordering, but it was not the single ordering. Like for some distance, the atoms will be arranged in this way. After that, maybe the atoms were arranged like this. So here in the small region, there is ordering. Here the ordering changes. So this is a polycrystal with smaller single crystals inside it. Okay, so these are different arrangements. Now coming back to the question why we are choosing this particular, because the electromagnetic wave spectrum is very long, from very few angstrom to a very large wavelength of radio wave and all. So why we choose X-ray? Because if you know this diffraction, when I was a TA for this experimental physics 2 course, experimental physics, yeah. So there we had discussed a little bit of optics, and we were talking about diffraction, which is a technique that when we consider we talk about light wave, then we had seen that light wave bends. If light is coming, it bends around very small objects or obstacle. Okay, but that diffraction or bending of light can only be seen when this size of this obstacle is comparable to its wavelength. Otherwise, if it's too big, then light will just pass simply. If it's too small, then also it won't show diffraction. So for diffraction to be seen, the obstacle has to be comparable to the wavelength of the light. This same thing we need here when we want to investigate our material. We want to see the plane, like we were discussing, we have different crystal planes, and plane is not actually there, like not a 2D sheet we'll see in our material. But what we are calling plane, if my atoms are arranged, say this is my cube, like part of cube, this is the face I'm seeing, and my atom on this particular face of this unit cell is arranged like this. So all these are in the same plane. So that plane we show like this, that yeah, this is 100 plane or whatever plane, and atoms are arranged. So here by our X-ray, the wavelength of X-ray and the wavelength of our, the radius of our atom is comparable. This is also about 123 angstrom, the radius of atom. So this, since it's comparable to the X-ray wavelength, that's why if we'll use X-ray and make it incident on our atoms or crystal unit cells, then they will show diffraction and give us information. And how we'll get that we'll see later. But this is the reason why we use X-ray and not anything else. Even if you incident any light, you will not be able to get the kind of information that we get from X-ray, because X-ray show diffraction, and from diffraction we get we can even get to know what is the lattice constant of this unit cell. You know, like we were before we were calculating packing fraction and everything, but how do we find, because atom is so small, how to find out the unit cell? So we use X-ray. X-ray shows diffraction, and with that we can do some maths and calculate what is the lattice constant of our unit cell. And further, we using this DHKL formula, if I find out A, if it's cubic, say, if I find out A, then I'll be able to find out DHKL. So all these information I can get, but the technique is through X-ray diffraction. There are more techniques now, but X-ray was the very important because it was the first thing that was we were able to use for this. Also, it's very popular, even though some new have come, like neutron diffraction, that also works similar, but they are first of all very costlier and rarely used for this. Mostly still very widely used is X-ray diffraction technique. Okay, so this was first the reason why we use X-rays for investigating our unit cell or crystal structures, because they have comparable length. Okay, I hope that's clear. So now, how do we get our X-rays produced? So we create a small vacuum tube. Inside we have a cathode where we generate very high energy electron by heating. There are different ways we can generate electron, but one way is that we heat a metallic filament or something, very giving lot of current. So we know heating works like this, right? The more current will pass according to the resistance of that object and the time for which the current is passed, it will produce heat. And after some time, electrons will be ejected out of that cathode or that metallic thing. And then we have, we have a big space in which we create vacuum. Why we create vacuum? Because we want We do not want that our electrons that are getting generated from the cathode is getting hit, it's getting collided with air or other gaseous particles, because it will lose energy and it will not do what we want it to do. So to avoid that unnecessary collision, we create vacuum in a small space. So that's why inside this vacuum arrangement, whatever be the shape, we have some metal which we call cathode. We give it supply voltage and supply current, and then electrons ejected from this. We have something negatively charged, so positively charged, sorry, this is cathode, this is anode, and then electrons will be, because they will go to positive high voltage place, they will accelerate here. And when they accelerate here, what happens here is, okay, let's first understand what happens here. So in the first class itself, if you remember, we were talking about principal quantum numbers, and we had seen that when we have atom, we have positive core, which we call nucleus, which has neutron, positively charged particle, and positron, positively charged particle. And around this positive core, the electrons are moving. In classical physics, we say electrons are orbiting. In quantum mechanics, we say electrons have probability to be found. So, but not going into that discussion, just like there's nothing wrong in assuming that electrons are there in this orbit, and depending on the rule that first shell can only have maximum 2 electrons and next 8, and like that. So electrons are arranged around here. This is K shell, this is L shell, and after that we get M shell, and next N, and so on, and they have their own energies. So what happens when I told this, from this cathode, the with the high energy electrons that are ejected will come and hit this another metal, and that metal will have atoms like this. Now when this highly energized electron comes and hit this anode's atom, then what happens is it knocks, so that outside electron comes, that just came out of cathode, and since there is no air and other unnecessary particles, so no unnecessary collision, it will simply come and hit here. When it will come, it will knock out the electron from this atom. The energy is so much, it will be able to overcome the attraction energy and throw it out of the atom. When it will transfer that energy to this electron to throw it out of the atom, it will lose energy. It will just fly off. But now, since there is a vacancy here, the electron from higher energy levels will come down to fill that gap or that vacancy. When that happens, if say from L shell, because say this electron came and it knocked the electron from K shell. Now K shell has a vacancy. Now if the immediate next shell, which is L, from that electron goes to K shell, then we know that energy level is proportional to n square. N is the principal quantum number. So energy of K shell, because K shell has n is equal to 1, L shell has n is equal to 2. And since energy is proportional to n square, that means this will have lesser energy than L shell. That means when electron from L shell is coming to K shell, it will emit some energy. Because energy, we had discussed, can neither be created nor destroyed, it can only be transferred. So what happens here? The electron, when comes from L to K shell, the excess energy will be given out, and that is given out in form of X-ray, because this energy difference is correspond to this X-ray energy. So that's why we get X-ray out of it. This is the typical way how we get X-ray. This electron coming here may not need to be always hitting this. Actually, that also depends what kind of X-rays we want. Say if the electron is coming and hitting the K shell, and K shell electron is going out, and due to some reason instead of L electron, M electron is coming and going to K shell. So yeah, so one thing, when L electron goes and fill the K shell, that the kind of X-ray that comes out, because all these have different energy gaps also, because I told you it's n square, so the energy gap is not linear here. So the energy difference between K and L shell is different. Energy difference between L and M shell is more. It's not equal. Okay. So the energy, if the electron from M comes to fill K, when L to K the electron comes, that gives another kind of X-ray that we call K alpha X-ray. And when from M to K the electron comes and fills the vacancy, we call it K beta. K alpha, K beta X-rays. These are all X-rays because their range is still falls in this range. So they are still X-ray, but inside X-ray, under X-ray also, they have different category because their energy is little different. I hope this is clear. If you have doubt, you can ask. I'll repeat again, but I hope if I could make it clear. And if similarly, as I said, so electron, depending on how much energy it had, it may not go and kick out the electron from K. It may hit and kick out the electron from L shell. Then of course K electron cannot go up because they don't have sufficient energy, but from higher energy electron can come and take this space. Then they will be called, so if I am knocking out electron from L shell and from M shell electron is going to fill up the vacancy in L, then it will be called L alpha. Same way from N to L, if this is happening, it will be L beta. So we have different kind of X-rays, and these energy levels also, it depends what kind of atom we are talking about, because different atom energy also depends on atomic number. There's like a lot of terms here, so that's why I'm using proportionality sign, that it depends on the principal quantum number or the shell number. Also it depends on the atomic number, that means what kind of element we are talking about. So corresponding to different kind of element we are using, energy difference will be different. So like usually commonly used X-rays is of wavelength 1.54 angstrom. This is a very commonly used X-ray wavelength, although I told you, right, the range goes from 1 to 10 angstrom, but a very commonly used is 1.54 angstrom, and this particular wavelength we get from copper. So we also call it copper K alpha, because when we use copper element and the electrons are kicked out from K shell, then L shell electrons go and fill that vacancy, and as a result emits out some energy in the form of electromagnetic wave, because the range of wavelength is this, that's so it's a X-ray electromagnetic wave, and we call it copper K alpha. We also may get copper K beta, but we'll see, we want only particular wavelength to get clear understanding of what kind of diffraction we will discuss, and Bragg's law which will come. So you will get to see we need particular wavelength. So when we want something particular wavelength, we don't want that all kind of different K alpha, K beta should be coming out. Then we will not be having a particular. When we have a particular wavelength, we call it monochromatic. As the name suggests, monochromatic. So for our measurements, we usually want monochromatic wavelength. As the name says, mono means one, single, chromatic means color. So we know color, energy, frequency, these are all related. So monochromatic means single color, means particular energy, particular frequency, particular wavelength. So we want monochromatic X-rays usually to get clear information. So this was like about a small understanding of how we obtain X-rays, because we need it to be emitted. We generate high energy electrons, they go, they emit, they hit this copper rod. Like here in this figure, it's like there's a copper rod. These highly energized electrons hit them, and to fill the vacancy in the lower shell, the electrons from higher shell come and occupy, and as a result the excess energy is given out in as X-rays. Okay, now yeah, this is also the same thing with more detail, but so this is how it is. Now as I told, we have K alpha, K beta depending on which electron from which shell are coming. So it's seen that when from L to K electron goes, we get K alpha. When from M to K it goes, we get K beta. It's been seen K alpha transition happens more. So intensity of K alpha is seen more. So that's why among K alpha, K beta, we usually prefer K alpha to get better results. So now next is what different kind of methods we have. First, let's understand. Now we understood what are X-rays, why we use them, and how we produce them, a basic understanding of how we produce X-rays. Now let's see how we, like, what is the working principle behind X-rays working and how we get information from making an X-ray incident on a unit cell or our crystal. So what happens is, this law and this method was given by two scientists, actually, father and son pair. So they assumed few things, and based on that they gave some rules, and when they did the experiment they got satisfactory result. So whatever the rules or models they hypothesize, which we usually do always in science, we think some model, and when experimentally we find the result according to that model, then we accept it as the theory, the correct theory. So what Bragg he said that we were talking about, right, that we have atoms arranged on planes, and then we have parallel, all these planes are parallel, they are all parallel to each other, and they all have atoms arranged on them. Okay, this is how we assume the arrangement. Now what Bragg like what's postulated or assumption or model, the rules he considered in that model is that these atoms, instead of seeing them as individual atoms, he said that let's talk about planes. Instead of talking about individual atoms, let's consider these atoms are making one plane, this is another plane. So like our priority is to concentrate on planes here. Instead of atoms, let's talk about planes. So these are the planes, say 100 plane or 110, whatever. There's some kind of planes. So instead of focusing on atom, he focused on planes. Next thing, he said, like in optics we see, if I have some mirror, we talk about light being incident on it, right? And then what is the incidence angle? When if we make normal, this will be incidence angle and this will be the reflected angle. And we know from the law of reflection that angle of incidence is equal to angle of reflection. So here we use a mirror or any reflecting surface. So taking analogy from similar situation, he said that these planes are also like mirror planes where our X-ray will be incident. See, if I'm giving this side view of these planes, okay, atoms are there, I'm not drawing, but these are just because I told their assumption was to focus on planes. These are side view of these planes. They are actually this whole, but let's just see it from side. So they said, let's consider these are our mirror, and then if I'll be incidenting X-ray, then they will also show reflection. That is, the angle of incidence will be equal to angle of reflection. And also they will follow some particular rule for this reflection, which will be like, because the reflection, like for optics we were saying that this incident light and reflected light, they are in same plane. I hope you understand. Like this if I how to explain, it's difficult in 2D, but these are in same plane. This normal, this incident angle, everything is in same plane, but that is not here. I mean, the light, if I give you top view, then being in same plane means incidence angle also came along this line and reflected also went along this line. Incidence also came along this line, reflected also went this line. It's difficult to show in 2D, I'm sorry, but I hope you understand. But here what's happening is, there may be various direction it could be going, even though it follows 2 theta. What I'm saying is sideways. So only that, it's similar as diffraction that I was telling why we use X-rays, because from the atoms it will show bending, which is diffraction, and after that bending or after that diffraction, whatever is diffracted and comes out, okay, leave that part, it's difficult to describe, but maybe later or in the lecture, I think the professor also tried to explain cone and other things, we'll see later. But okay, so first thing was this diffraction that is happening, this X-ray is incident, and from the plane, or actually from the atom, it's bending means it's not going to actual path, it's changing its path, so it's bending, and it won't happen to any random light, no, it will happen only to X-rays, because I told you the diffraction only happens when the wavelength or the length dimension is comparable. So only when X-ray of similar comparable wavelength as the size of atom is incident, then we'll see this diffraction, which is similar to reflection. Why? Because in reflection also we have some mirror plane kind of thing, light or electromagnetic wave is incident and reflected. The same way we have X-rays incident and they reflect because the angle is same. This you can consider, or this you can consider. So after diffraction, because when we used to talk about optics, we just used to have one surface, but here we know we have parallel surfaces, which we are called family of planes. So some part of X-rays go penetrate and they get diffracted from the next layer of atoms. Not all get diffracted from the very first one. So correspondingly, we have all these diffracted from different planes, from these parallel planes, and then when after diffraction they interfere with each other. Interference also in experimental physics we had discussed happens when there is constant phase difference between two similar source. So when there is constant phase difference, we get interference which has constructive and destructive interference. Similar here, if the phase difference between the X-ray reflected from first top plane and the X-ray diffracted from the next plane, they have constant phase difference, then they may show constructive interference or destructive interference. And the rule to get constructive interference given by Braggs, this also he took inspiration from what we do for grating. The optical grating, for that we define what is the condition to get constructive interference. From similarly, he also took 2D sine theta is equal to n lambda. This is what is the rule, the diffraction condition he gave taking inspiration from optical grating, where we discuss that we have grating like this, and this is the length of the obstacle, and light coming from here, it will bend, and it will on the another plane, it will give constructive or destructive interference, and we'll get darkness, brightness like this. So we also have a condition there, and similar way we have a condition here. So it's almost like same whatever we were discussing in diffraction, but there we were using light waves, here we are using X-rays. So this is, they didn't derive it or anything, they just gave it, and when they conducted experiment, it was fulfilling this. Okay, so what this is, 2d sine theta is equal to n lambda, where lambda is the wavelength of our X-ray that we are using. 2 is just number, d is the distance between the HKL plane. Like here I'm using these family of planes, they will have same distance throughout, right? Because they are 100 plane, they will be equidistant. So the distance between these planes is what is DHKL. It's similar like the grating, like gratings had this gap. The similar way, this is grating element, we can say. But this is interplanar spacing. So this is interplanar spacing. Now theta is the angle of incidence, or sometimes we take angle of this glancing angle or grazing angle. So like angle of incidence usually is taken like this. If the incident is this, then this is angle of incidence from the normal. But if this is the normal and the light wave is coming like this, and instead of taking the angle from the normal, we are taking the angle from this surface, then that is called glancing angle. This is called incidence angle, and this is called glancing or grazing angle. So here for X-ray, we usually take this theta as grazing angle or glancing angle instead of incidence angle. So this theta is our this angle of diffraction also you can call, because anyway this will be equal to its, this is also equal, that's why we call it, this is similar to reflection, because in reflection also angle of incidence is equal to angle of reflection. Here also it's same, so that's why it's also called X-ray diffraction, or basically it's diffraction, but because it's this atomic plane or crystal plane are acting as mirror planes, and they are in a way reflecting the X-rays with equal angles, so it's similar to what we see in optics reflection. So that's why we also sometimes use the term reflection. X-ray is getting reflected from this crystal plane. So these two terms, diffraction, which is actually happening here, but also is interchanged with using reflection, because these planes are acting as mirror planes, and we can say they are reflecting the X-rays which are being incident on them. So that's why both terms you will hear is being used, and in a way they both are correct. So that is just to clarify this, because of course we call XRD, the technique is in short called XRD, and we call X-ray diffraction. But still you should now be clear why still you may hear people using reflection term as well. Okay, so this is theta. N is the order parameter. Like I told, in diffraction we used to see primary peak and then secondary peak. So n is equal to 1, n is equal to 2. Order we used to say, this is order 1, order 2. Similar way in XRD also we get different order. So this is order X for X-ray peak. So this, as I told, this taking analogy from that interference we see in optics, the same way they gave this formula, and with experiment it was found to be correct. So now let's see how we, little small derivation we have for this. Before this, just to make it clear so that you can find this formula yourself also, it's not a big deal, just to make it clear. So the small derivation again is like we know we have actually mirror, the crystal planes with atoms, but for derivation we just consider the, we consider the planes like this. There's some parallel planes, and I'll derive my Bragg's law for this. So if I draw a perpendicular to these planes, okay, and just a minute. Okay, and then my X-ray is incident. Oops, sorry. It's not good. Okay. Yeah, better. Okay, so this is incident X-ray. This is diffracted X-ray, and the angle is same. It's found to be same. That's why I told we call it reflection. And here we consider this glancing angle. Let's call it theta. So reflected also will be same, theta. And this will be 90 minus theta, this will be 90 minus theta. Basically, even this is same, even this is same. But usually in XRD, we consider these glancing angle or grazing angle. So the X-ray reflected or diffracted from the first plane will go like this. Then I told there will be some X-rays, not all will get diffracted from the first plane. Some will go deeper, and from the next plane they will diffract. Some will go even deeper and diffract from there. Some just transmits also, and they don't go penetrating all the way down. Only like there is a few nanometer range, angstrom range. I don't remember exactly range, but only up to that they uh, go inside and diffract. But that much layer itself is sufficient for us to get this result. So we don't need to bother. So X-rays when come like this, they go here. So what happens here is, you can see the first one covers this path. The second one, because it goes this extra depth, which is the interplanar spacing, the X-rays going to the second plane and diffracting, they are going this extra distance inside, so they cover some extra path compared to the first one. The third one here, it is covering some extra path compared to second one and compared to first one. So we have to find out that extra path difference, because the law that Bragg gave was that to get constructive interference, like all these diffracted waves will go and show interference, but that will be constructive or destructive. So to observe them, we need constructive interference. And he said that to get constructive interference, the path difference between these two diffracted X-rays, the path difference should be integral multiple of wavelength. This is that integral or order parameter that we call it, should be an integer, so that we see constructive interference. So path difference should be integral multiple of the wavelength of incident X-ray that is being used. So how we get this Bragg's law from this? Let's find out the path difference, that extra path. Change color. The extra path that is being covered by this second X-ray is, if I drop a norm, if I drop a normal from this point on this second X-ray 90 degree, and on this, why this happens, and this also, this is 90 degree, then if I find out this length, this extra length, this is the path difference, because till here to here it's same, till here to here the distance is same, this is the extra path that they are covering. Okay, and to find out this, we will do some trigonometric maths here. Okay, let's see how we do this. So, to find out this, let's give some naming here. What I want to tell is, let's say this center one, let me call it O point, and this I'll call Q, and this I'll call R, and this point let me call P. So this is O, this is Q, this is R, and this is P. Okay, now you see one thing, this X-ray, they are all coming parallel. Monochromatic source coming all parallel. So it's making theta, means everywhere it's making theta. That is how it is. Incidence at the same angle and reflection also same angle. So here if you see carefully what I have drawn, this, okay, this is theta, then this angle will also be theta. Why? Because vertically opposite angles are equal. Anywhere, any kind of line is there and another line intersects it, then this vertically opposite angle are equal. This vertically opposite angle is equal. Okay, so here you see this is my plane. Let's call 1, this is 2, this is 3. Plane 1 is getting intersected by X-ray at this point. Okay, and the angle theta is this, then this angle is also theta. Let me expand this triangle. Okay, the triangle I am talking about is this. This is the X-ray incident on this plane. Okay, and this is the normal here. This is the extra path difference I am trying to calculate. This I've just expanded because it was getting very congested here. This is 90 degree, this is 90 degree, this is Q, this is P, this is R, this is O, and this is X-ray incident, this is X-ray reflected, and I told that this is theta. That means this is also theta because vertically opposite angle I told you. Now next is, if this is theta, then what is triangle O? Let's call this A. Okay. If angle OAQ is theta, then angle, what will be this angle? Because ultimately what I want to show you guys is, or let's find out, because it will help us in finding out this QP. I want to find out the path difference QP. So one thing is clear, the angle is incidence on the crystal plane at angle theta. So this angle will also become theta. I hope this is clear. If you see very clearly, this is a perpendicular I have drawn, means this is 90 degree. Shit. What? Yeah, okay. Let me just save and go away. Yeah. So this is 90 degree. I don't understand. Sometimes why it happens? I don't know. But anyway, so this is 90 degree, right? If in this triangle, this is a right angle triangle, AOQ. In this right angle triangle, if one angle is theta, another angle we want to find out, let's call it AOQ, and this angle is 90 degree because I draw perpendicular to this, right? So this angle is 90 degree. If you guys have any doubt in any step, you can please unmute and ask. I'll clarify again. We have time to understand this. But if you understand this, then you will be able to get this expression for Bragg's law anytime. So that's why I'm telling you each and every step very slowly. So this angle theta, this angle 90 degree, this angle we want to find out, and for a triangle we know the sum of all the three angles is equal to 180 degree. This is known for any triangle. If this is true, then I can see angle AOQ will be, this will be 180 minus 90, that will be 90 degree. Okay, that means angle AOQ will be 90 degree minus theta. In this triangle, one angle is 90, one angle is theta. So next is 90 minus theta. We did the maths and we found this angle is 90 minus theta. Okay. Now, let's see another thing. In this triangle, this is also a right angle triangle, right? This AOP, here this is a 90 degree because I told you this is my plane and I am drawing a normal on it. So this is also 90. That means this is also 90. Now in this angle, in this triangle AOP, okay, this AOP, one angle is theta, this angle is 90. Actually, we don't need this also. So what will be this angle? Here in triangle, okay, that is fine. In triangle AOP, angle AOP is 90 degree, one is theta. So angle QOP will be what? AOP is 90 degree, and okay, AOP is 90 degree, fine. Angle AOP is 90 degree, that is clear because I have drawn normal to this plane. So angle AOP is 90 degree. Now if you see, angle AOP is made up of angle AOQ and angle QOP, right? It is made up of these two angles. It is made up of angle AOQ and angle QOP, or you can call it POQ, both are same. So AOP is made up of these two angles. So their sum is still equal to 90 degree. Now we just now found that angle AOQ is 90 degree minus theta. Angle AOQ is 90 degree minus theta, and angle QOP we still don't know, but the sum is equal to 90 degree. Now from here, if I want to, this 90 cancel, and this minus theta, when it will go to right side, angle QOP will be equal to theta. That means this angle QOP means this is theta as well. So all did this small 2-3 steps I did just to tell you that this angle is theta. Okay, the X-ray which is incident is making angle theta. This is theta, this is theta, also this is theta. But how do we get to this point? To explain that, I told you that how this is theta and how this is 90 minus theta and how this is theta, okay? Otherwise, usually it's just directly given that if this is theta, then this is also theta. To tell you how we arrive at that, I explained you this way. So if you still want to ask, you can ask, or if you need to see it again, of course these lectures will be available on the YouTube channel. You can go through it again. It's basic step I think, but just to make it clear that how we get that. In this triangle QOP, this angle is 90 and this is theta. And now we'll use this to find out what is this QP length, which will be our path difference. Okay, so how we get that? This triangle QOP, this is 90 degree, QPO, Now using trigonometry, we know sine theta, this is theta, right? That we just did, this is theta. Sine theta, we know it will be perpendicular upon hypotenuse. That means QP upon OP. What happened? QP upon OP. Let me go to next slide. So in this triangle, sine theta is QP upon OP. And QP is what? QP is the path difference I want to find out. Let's call it what? X. Okay, let's call it X. This is the path difference I want to find out, divided by OP. Now OP is this, and that is the interplanar spacing distance, DHKL. This is DHKL, the interplanar spacing. So I see my total path difference is this QP plus PR. This QP plus PR is the total extra path that the second X-ray is traveling. So total QP plus PR is the total path difference. Just now I found out QP, if I just keep X or I call it QP, whatever, okay. So that will be, this will be sine theta DHKL, okay. This is X. Now this PR, same maths when we'll do this side also, we'll get same, that this PR is equal to sine theta DHKL. So the total path difference, which is QP plus PR, will be sine theta DHKL plus sine theta DHKL. That means 2 sine theta multiplied by DHKL. And since the rule was that to get constructive interference, the path difference should be integral multiple of lambda. Path difference I found out is this, and it should be integral multiple of lambda. So this is how we get this Bragg's law. So the assumptions to get to this Bragg law, assuming that we have parallel planes like this by which the X-rays are getting reflected, all these are inspired from what we see in optics, but we see that we can even get the expression after taking those assumptions, but after putting this kind of maths here, we could get this Bragg's law in this way. So this is how we get 2d sine theta is equal to n lambda. Our n is integer. This is how we get our Bragg's law. So I hope the little derivation that I did is clear to you guys. And now we'll move on to what kind of different techniques of X-ray or working methods of X-rays are there to find out about these. One more thing before this is, so when we like we talked about how we produce X-rays, and we saw that we get K alpha, K beta, or maybe L alpha, L beta also. Then there is something known as filter that we use. That is another big like detailed concept we don't need right now, but there is something known as filter that we use to choose particular wavelength out of all this different. Otherwise, if there is mixture of all these X-rays, then we call it white X-ray. Because why white X-ray? Because like we know white light is mixture of lot of wavelengths, right? White light when splits, it gives to those 7 different colors: violet, indigo, blue, green, yellow, orange, red. So white light consists of all these lights. So same, if I'm talking about these different X-rays source, then we call it white X-ray source. And if using some filter, I particularly choose some particular wavelength, then we call it monochromatic X-ray. Or particularly we can call it by that name, K alpha X-ray, K beta X-ray, whatever we have chosen. So how it looks is that wavelength when it's not filtered out, it's something like K beta peak we see, K alpha peak we see. This is K beta, K alpha, the X-ray peak aspect as a varying with wavelength. Okay, and then when we filter out, we choose particular wavelength or something. Okay, so the different methods are, one is Laois method. The pronunciation is very different because they are not Indian, not foreigners, researchers. So the name pronunciation may not be correct, but okay, this is his name. This is Laois method we have, where we talk about, we'll see. But here what we say, we fix the, like I showed you, right? We have planes and we have incident X-rays which get diffracted and then they interfere and gives us constructive and destructive interference. So here we have theta, and this is the interplanar spacing d and the wavelength that we use for the X-ray. These three parameters we need to get our condition. So in Laois method, the technique is to fix this theta and vary lambda. So varying lambda means we are using different lambda. So we use a white X-ray source to do Laois method. We use white X-ray source. Okay. And another technique is rotating crystal method. In this method, again the parameters, important parameters are d, theta and lambda. Rotating crystal method, the way is to fix the wavelength, means we'll use a monochromatic X-ray source and we'll keep theta variable. Means we'll be changing this theta, different theta we'll use, theta, like we'll change this, different thetas we'll take. Okay, and we'll keep the wavelength fixed. That also will result in different diffractions. And third is way is powder method, it's called, or it's also called Debye-Scherrer method because these scientists gave this method first time, so it's also being called by their name also. In this also we keep lambda fixed, we use monochromatic X-ray and we vary the grazing angle to get all the peaks from all the possible. Why we vary and why we want to get all? Because like we know not only one family of plane is there in a crystal, right? We know, like if I draw this cube, this is my unit cell for some element. Z-axis, y-axis, x-axis. Now this front, if I say this is 1, 0, 0 plane, then this is 0, 1, 0 plane and the top one will be 0, 0, 1 plane. If it's cubic and the same arrangement of atoms are there, then all these three, in fact the opposite one also, all 6 will be family of planes in this case. family of planes, I'll get 1 0 0. It corresponds to all. Then there will also be 1 1 0, right? And 1 1 1 plane. So in one unit crystal, we have different families of planes. Not only this 1 0 0, we have 1 1 0, we have 1 1 1, 2 2 2, and like lot of pairs. So when the X-ray is incident and it diffracts and it interferes, it's not corresponding to only 1 0 0. Okay, so one thing more. This Lave method and rotating crystal method is used for single crystals. Means the arrangement is only in one direction. The arrangement of atoms is uniform. So here these arrangements will be on a plane, right? Excuse me. So here for single crystals we have these two techniques. Sorry. Where one, we keep theta fixed, that angle of incidence of X-ray we keep fixed, but we change wavelength. So diffraction condition satisfaction will change and we will get diffraction different from different plane. And for rotating crystal method, here instead of changing wavelength, we are keeping wavelength same, okay, but we are changing D is anyway same for one particular kind of unit crystal. I mean, like say it's iron crystal or NaCl crystal, then D will be same. So D is anyway fixed, but we can only control externally, we can change the incidence angle and the wavelength of X-ray source. So these are the only two things we can play around with. So in this, in Lave's method, we keep incidence angle or grazing angle same and we change wavelength. Correspondingly, we get diffraction from different D. Means different plane at different angle. When we keep wavelength fixed and change the theta, okay, we source X-ray source, and this is my plane of the sample. Then we change the angle of the source, okay, we take it from small angle to high angle, and so incidence angle, this is how we change. So we change the incidence angle, D of the sample is anyway fixed naturally. So corresponding to different angle, it will be satisfying the situation for different Ds. Right, D is same for 1 0 0. For 1 1 1 it will be different. But through I'm saying it's same means it will be this fixed for one kind of atom. But different planes have different D values, right? Like interplanar spacing for 1 0 0 will be different. Interplanar spacing for 1 1 1 will be different. So for different interplanar, depending on as I vary theta, the condition will be satisfied and we will get the diffraction corresponding to all the different planes. So these two methods are for single crystal where the arrangement is same, no change in arrangement of atoms. But powder method we use when we have a polycrystal material, then it's difficult to be, if I don't change theta, it's because the arrangement is not uniform throughout. Okay, there's small single crystal arrangement inside that whole thing. So I want to expose all these different planes. Now the plane is like this, so maybe here the plane is like this. So I want to expose to X-rays all these different, I told you X-rays don't go inside till deep. I want all these small crystals to be exposed to my X-rays. So one way is to grind this. Whatever kind of material we have, we usually grind them so that we get small particles. This is not atom, what I mean is small particle with different, maybe it's so small that only one kind of pattern, one kind of crystal is there, even that could be possible, or maybe it's not small but maybe two kind of planes are there. So we grind too small so that we can expose Now X-ray can be directly exposed to these, and then we'll get X-ray pattern from different HKL plane. And in detail, all these three methods, the professor has explained a lot and well in the lecture. So please go through there. If you still have doubt, you can ask me in the next session. But please go through those. He has explained all the three methods very well. So in Lave method, this is just to show you, we keep X-ray source, and then we have X-ray source, and then we have crystal. It's usually very small, but here we are showing it quite big. And then X-ray, when it reflects or diffracts, it gives spot on, we have something called photographic film. If it's at the front side, we call it transmission. If it's at the back, then it's called back reflection. And these spots, their arrangement tells us what kind of family plane, what kind of symmetry the unit cell has. So these things are there in detail in the lecture, because we need some time for discussing the assignment problems. This is rotating crystal method, the next technique. We have sample here, we have this collimating I am using. This is like to get monochromatic X-ray, because in second method we keep wavelength fixed and theta we vary. We vary theta by rotating this sample, and we keep lambda fixed by taking only one wavelength. And here we get like corresponding different planes. This again, you go through the video lectures please, you will see how we get these. And then we have powder method, where we get this conical things on the camera film, and from this we get to see how like this basically results in giving us at different theta what is the intensity of diffracted beams we are getting, corresponding to which plane it is. Like this, how much they are diffracting, that tells us corresponding to theta, it tells us. And then depending on that we get the intensity on this scale. So usually when we do experiment, what we get out of experiment is intensity of diffracted X-ray as a function of 2 theta. Now why we say 2 theta and not theta, this is also a very important question, is asked many times. So what happens is, when I have my planes like this, I have incident X-ray theta. Experimentally it's difficult to measure the angle between X-ray and my planes, crystal planes. Particle is so small, then we are talking about crystal planes. They are in angstrom order. This is very small. So it's experimentally very difficult to find out what the X-ray is making the angle with the crystal plane, and that too they are different crystal plane. So the easy way is, like the diffracted one, this will also be theta. We just saw they are like what we say, a reflection. So angle, grazing angle and diffracted angle is same. This is theta that we know. This we use a detector. We move the detector and we get the diffracted light, and that angle we know. That we can detect. Now, but this is also again crystal plane. This angle is same, but how to find out this angle? So instead what we do, from where we are incidenting the X-ray, I told you not all are diffracted. Some are absorbed and some are transmitted through the sample. Most of it is transmitted, small amount is reflected, that we detect with lot of sensitivity. So the transmitted light, that we know where it's, because we know this we can detect. Corresponding to this, so this is theta, because grazing angle is equal to diffracted angle. Also I told you vertically opposite angle is equal, right? This is plane, this is the x-ray, then this and this will also be theta. We had discussed just earlier. This is theta, means this is 2 theta. This, using detector, I can detect where the light is going, and then I can detect where this incident light, which is transmitting through the sample, is going. So this angle difference I can measure, and I can find out 2 theta. So although finding out theta is difficult experimentally, but finding out 2 theta is very easy. So that's why when we perform this X-ray experiment, instead of getting theta, we get from the experiment 2 theta. Then for our use, we take half of it and use theta. But experimentally, we get 2 theta, and that's why we always get the pattern in 2 theta. Always you will see. This is how we get the data. So this is the plot we get, intensity of the X-ray peaks and their broad thickness. They give lot of message. We have to analyze these peaks, but we get as function of 2 theta, and then we find out using, like we know, interplanar spacing. I told you, if it's cubic, this is the formula, right? We'll do some questions where we'll see how to find out. If I know that one peak is at this, then how to find out what is the lattice constant. This one relation we know, and another relation we know is this. Using these two relations, we can find out lattice constant. That anyway we are going to do in the coming problems, so I'll not tell you here. But this one thing, I hope I made you clear why we always get 2 theta on the x-axis and not theta. There is a reason for this, and the reason is this, that we cannot calculate theta, we cannot measure theta in this experiment, but we can easily measure 2 theta. That's why out of the experiment we get the data in terms of 2 theta. This is also very important question asked many times in experiments, but yeah, I just told you. Okay, so now let's focus on some assignment problems. So first question is, a plane intercepts, just a minute. So first question is, a plane intercepts crystal axis along A at z. Okay, so again, because they have not given anything else, so we'll consider a system where all the angles are 90 degree. So very bad drawing, I'm sorry. Actually, this digital pen is little difficult to handle, that's why this happens. All angles are 90 degree. This is, say, crystal axis A, this is B, this is C. Okay, now we have to find Miller index for this plane. This plane is cutting A axis or X axis, whatever, it's okay. A axis, it's cutting at 0.25 A. B axis, it's cutting or intercepting at 0.50 B. C axis, it's not cutting, it is parallel to the third axis, which is C axis. It's parallel, means it will be parallel, means it will intersect at infinity. So to find out Miller index for that plane, which is cutting A axis at 0.25, B axis at 0.5, and it's parallel to C axis, to find out what that plane is, to find out the Miller index for that plane, we have done this before. First step is to drop these A, B, C. Just take the number 0.25, 0.50 and infinity. Okay. Next step is to take reciprocal. So this in reciprocal, 1 over 0.25. This will be 1 over 0.5. This will be 1 over infinity. When we will solve this, we will get this will be, so it is like writing 100 over 25. So if I reduce this, it will be 4. This is like 100 over 50. So it will be 2, and 1 over infinity is 0. So the numbers I get is 4, 2, 0. Now although they are integer, but there is one step next is to reduce this to smallest number. That we'll do by dividing by 2. If I divide all these numbers by 2, I'll get 2 here, 1 here and 0 here. So this smallest reduced integer 210 put in parenthesis will give me the Miller index. 210 is the correct answer. Next question. Nickel has FCC structure with a lattice parameter of, usually we denote lattice parameter or lattice constant using small a. So this is the lattice parameter of FCC nickel structure. Find the interplanar spacing. We have to find interplanar spacing D between the closest packed planes 111 in the metal. So we have to find out D11. D11 is the interplanar spacing between 111 planes. This is what we have to find out. Since it's FCC structure means it's cubic. Okay, that means I can use this formula. This is H. Since it's cubic, I can use this. Since it's cubic and it's space-centered cubic, means all sides are equal, so I can directly use this formula. Otherwise, I have to use H by A whole square, K by B whole square, L by C whole square if all different sides have different length. But since it's FCC, all sides are equal, which is A, and I can directly use this formula. Now, so D111 will be, A is given 3.52 angstrom and under root HKL. H is 1, K is 1, L is 1. So 1 square plus 1 square plus 1 square. This will be 3.52 angstrom divided by 1 square plus 1 square plus 1 square. This will be 3, right? This will be 1, this will be 1, this will be 1. That means 3 root 3. When we'll do this, I'll use calculator. Because in exam also, when you have such questions and you need calculator, because the exam is always online, you get online calculators. That I can tell you at the end of this whole, all the sessions. We may have an extra session where I can tell you how to use that online one. But you will have some calculator. So you can use this, you don't need to do it manually. 3.52 divided by root 3. It's 2.03227 angstrom. The options available here which match closely with our answer is this, option C. 2.03 angstrom is the interplanar spacing between 111 plane. Okay, next question. This is a very interesting question. Pay attention. So iron has BCC structure below 910 degrees centigrade and above 910 degrees centigrade it takes FCC structure. We know BCC means all the corners are occupied and body center has one atom. In FCC, corner we have atoms at the corners and then all the faces. So below 910 degrees centigrade it takes BCC structure and above 910 it takes FCC structure. Assume same atomic radius in both structure, that both BCC and FCC the atomic radius is same. Find the percentage change in volume when the metal undergoes structural change. We have to find out when the crystal was in BCC, what was its volume, and when it changed to FCC, what was its volume, and then we will find out the change in the volume before and after. Okay, that change we need to tell if it reduced, it increased, and by how much. Okay, so for this, we know first of all that for BCC, what is the relation between lattice constant and the radius of atom? For this, you should remember we have atoms at corner. So body diagonal we consider. In BCC, body diagonal, atoms on body diagonal are touching each other. Okay, and body diagonal, this we had discussed several times. I hope by now you don't need to derive. By now you should just remember so that it will be easy. That body diagonal, length of body diagonal is root 3 times A, and this is 1r, right? R, this is R. So this is equal to 4r. In BCC, the atoms on the body diagonal are touching. So we find out the relation between lattice constant and radius of atom by this. This is the relation for BCC. And from here we see that lattice constant is 4r by root 3. Okay. Now, so this is the lattice constant. So what will be the volume of the unit cell? It will be A cube, right? So it will be the cube of this whole, 4r by root 3. This will be the volume when it was in BCC form. Now for FCC, we know for FCC, we have atoms at the corners and the one on the phase diagonal. So all these phase diagonal ones are touching each other, and phase diagonal is root 2a is equal to 4r. So a is equal to, we should call it a1 actually, because the lattice constant is changing in BCC FCC. Let's call it a1, and radius we have been asked that it's same. Let's just call it a2. Okay, a2 will be 4r by root 2. In this case, volume will be a2 cube, which is 4r by root 2 whole cube. This is the final volume. Now one thing, some slides here. Yeah. So the thing to notice is, this is the volume of FCC unit cell, this is the volume of this is the volume of BCC unit cell, this is the volume of FCC unit cell. But this is, we have to be careful here in BCC, what are the total number of atoms in this unit cell? In BCC we know we have atoms at the corner, so in total we have 1, and then there is 1 atom in the body center. So total 2 atoms we have in BCC. In FCC, we have contribution from atoms at the corner, 1/8, and we have 8 atoms. Plus we have atoms on the face center. We have 6 faces and half contribution. So in total we have 3 plus 1, 4 atoms here. So for BCC we have 2 atoms in one unit cell. For FCC we have 4 atoms in one unit cell. So how much volume one atom is occupied? Okay, so for BCC, because below 910 it was BCC, so V1 I found is, if I take cube of this, it will be 4 cube is 64, and then R cube divided by 3 root 3. Okay, for FCC V2, this will be cube of 4 R cube divided by 2 root 2. This will be 64 R cube divided by 2 root 2. But it has 2 atoms, this has 4 atoms. So volume occupied by one atom for each atom or for one atom here will be 64, basically V1 divided by 2, and here volume occupied by each atom, this will be V2 by 4. So this is the volume for which we need to find out the change. Okay, this we need to be careful. So now when I want to find out the change in volume, the final one, let's call it initial, because how much the radius is same but the volume occupied by atom is changing in these two different structures. So change in volume is final minus initial divided by initial and then multiplied by 100. So here that means B2 by 4, which is this 64 r cube divided by 2 root 2 divided by 4 minus 64 r cube divided by 3 root 3 multiplied by 2. Okay, divided by this whole 64 r cube divided by 3 root 3 and multiplied by 2. When we will do this maths, see all the 64 will be cancelled because we have it in numerator and denominator. All the r cube will be cancelled. Okay, so what we'll be left with will be, oh, let me go to next slide. So percentage change in volume will be 1 over 8 root 2 minus 1 over 6 root 2. Wait a second. 1 over 8 root 2 minus 1 over 6 root 2 divided by 1 over 6 root 2. Yes. So when we do this, when we do this, one over 8 root 2 minus 1 over 6 root 2 divided by 1 over 6 root 2 and then multiplied by 100, of course. Then we'll get, this is smaller than this, so the answer will be, this actually will become minus 0.0814 multiplied by 100 means minus 8.14%. So this is the correct answer. So the volume is reducing, volume is contracting by 8.14%. A is the correct option. So we have to be careful when we calculate the volume. We have to check here how much the volume is corresponding to one atom for both the situation, and then we have to find it out. Otherwise, we won't get the correct answer. Okay. Okay. Next question. Calculate the value of cation to anion radius ratio for CSCl structure in the limiting case when the anions are as close as possible, where R is the radius of cation and R is the radius of anion. CSCl structure can be seen as BCC lattice. So BCC lattice, we know that we have atoms at the corners, but here instead of atom we are talking about one molecule, CSCl. Okay, it's not only iron unit cell that all corners and body center is occupied by iron atom. This is a CSCl molecule. So what happens is, for this it can be taken as BCC, but what happens here is this CS plus cation and Cl minus anion, either we can consider cation on all the corner and then this anion in the body center, or vice versa. Anyway is correct. So here if I consider that, let's say all the cation is on the corners, CS plus, and then the Cl minus will be in the body center. So you can see overall it will be a neutral crystal, right? Because the CS plus, all the corners, they will contribute in total 1, and this anion in the body center, it will also contribute 1. So overall it will be charge neutral, this unit cell. So this is correct. So this is the arrangement, and Now we have to find out the radius of cation to anion. So cation radius it is small r, and anion radius which is capital R. We have to find out the ratio of these radius. Now let's say the lattice constant is A and its BCC, means all sides are equal. Let's call lattice constant A. Now we need to find out the relation between radius of these atoms and lattice constant that we always do. For BCC, when we do this, now its BCC means the body diagonal atoms are touching each other. Also, if you see, we have been told we have to consider limiting case when anions are as close as possible. That means anions or cations are as close as possible, means even here we can consider that it's almost touching here also. Okay, it's as close as possible. That means basically the cations are touching each other and anion is very small and it is residing in the gap in between. Okay, this is the actual how CSCl atoms are arranged, that cations are like this and in the in between gap the anions chloride is sitting. But okay, so in this body diagonal we will find out what this is. For cation we have small r, for anion we have capital R. So we'll find out relation small r and then capital R, small r. So r plus r plus r plus r is body diagonal length. I told, now we remember that it's root 3a. That means 2r plus 2r is equal to root 3a. That means the relation between a and these r's is a is equal to 2. I'll take 2 common, divided by root 3 r plus r. This is the relation between the radius of these atoms and the lattice constant. This we found out. Now next step is, since I told you we were asked to take the limiting case when these ions are as close as possible, means even here they are touching almost each other. That means I can take, this is A, of course lattice constant. In this I can take r plus r is equal to A. So 2r is equal to A. Okay. Okay, now next is, okay, I need yeah. So these are the two relations I found out. Now this r plus r plus capital R, this r plus capital R will be root 3a by 2, root 3a by 2, and from the second relation I found out r is equal to a by 2, or a is equal to 2r, a is equal to 2r root 3r. So the relation will be r is equal to root 3r minus r. Root 3 is usually 1.73. So this will be 0.73 r, use capital R. So we had to find out the relation between small r and capital R. So that will be oh, I did one mistake, sorry. Cation radius is small r. Cation radius is small r. Okay. I did So the relation of R by capital R, this actually should have been, this is where I made mistake. It was, they were telling about anion, right? That anions are as close as possible. Anion is capital R. Okay, so anion is capital R. So this would be the relation. A will be 2 times capital R. Okay. So it will be small r is equal to this capital R. So small r by capital R will be 0.73. So the matching answer will be this. This is the correct answer. I missed this point that they said anions are as close as possible. So I had to take the radius for anion, which was capital R. Okay. Next question. Calculate the density of CSCl given that radii of CS plus ion. Okay, we have been given radius of CS plus ion and Cl minus ion. 1.81 angstrom. For CS plus, radius is 1.65 angstrom. Okay. Atomic weight is given. Consider one formula unit contained within the unit cell. We have to find out density of this unit cell. Okay. So again, since this is CSCl and CSCl we just now saw, it takes BCC, and in BCC the relation is this. A is equal to 2 by root 3 R plus R. A is equal to 2 by root 3 and sum of these radius, which is 1, like radius of CS plus and radius of Cl minus, 1.81 and 1.65. This is the relation between radius of these atoms and the lattice constant. Because we need to find out density, we need volume, lattice constant is this. Okay, so when I'll do the calculation, we'll get 1.81 plus 1.65 means 3.46. Further, when we'll get 3.99 angstrom because the radius are in angstrom. So this is lattice constant. So the volume will be AQ. But to find out the density for a molecule, our formula is this. So to find out density, the formula is number of here we have whole molecule in this unit cell, and we have been told to consider one formula per unit cell. So usually it's number of atoms, but here we have one molecule in the unit cell, so number of molecules multiplied by the mass, which here will be atomic weight, divided by Avogadro number, because atomic weight we express in gram per mole, and we know in 1 mole we have Avogadro number of particles. So this is how we write the mass divided by the volume. So this is the formula. So when we'll put number of molecules was 1, because we have to consider, as per the question, we have to consider one formula unit within the 1 unit cell. So CSCl, only 1 molecule is there. Then atomic weight. Now atomic weight we have been given for CS and Cl 132.9 plus 35.45. So 132.9 plus 35.45, and these things are in gram per mole. So to get per atom, we'll divide by Avogadro number, which is 6.023 times 10 to the power 23 divided by A cube, and A is 3.99 angstrom. So A cube will be 3.99 this whole cube, and also angstrom, when I put it into meter, 1 angstrom is 10 to the power minus 10, so cube of this also. When we do this, when I do this calculation, this is also gram per molecule, gram per mole, right? So gram to kg, because our answers are all in kg and this atomic weight is in gram per mole, so I need to convert this also into kg. So when I convert gram into kg, it will be multiplied by 10 to the power minus 3. When we solve this, the answer will be 4.4 times 10 to the power 3 kg per meter cube. This will be the density of this unit cell. Correct answer is option A. Okay. Next question is, cesium metal, which has atomic weight 130, means 130 gram per mole, has a cubic unit cell with lattice constant of 6 angstrom. If density is, density is already given, which is 2 gram per cc or centimeter cube. It's same thing. Determine what type of crystal structure this is. Okay. This time we have been given lattice constant, we have been given density. If we can find out the volume, and then maybe we can see how many atoms are there in that volume. And because we already have knowledge of simple cubic structure has total 1 atom, FCC has total 4 atoms, BCC has total 2 atoms, and hexagonal we are not sure, but let's see. Okay. So when we know to find out density of unit cell, we need number of atoms multiplied by atomic weight divided by Avogadro number multiplied by volume. When we put these things, number of atoms per unit cell, number of atoms per unit cell we have to find out, and atomic weight is given, which is 130 divided by Avogadro number, which is 6.023 times 10 to the power 23, and the volume A cube, A is 6 angstrom, so 6 times 10 to the power minus 10 whole cube. Okay, density is given, which is 2. So when we'll do the maths, we'll get N is equal to, density, which is 2 times this Avogadro number 10 to the power 23 multiplied by 6 to the cube and 10 to the power minus 30 divided by 130. When we'll do this calculation, we'll get N is equal to this 6 times 6 times 6 is 216 times 2 divided by 130, okay, times 6.023, 20, this is, I'm getting 20, and then this is 10 to the power 7. Okay, so this is in gram centimeter cube. So I changed in meter. If I change it into, so 1 angstrom is 10 to the power minus 10 meters, but density is in centimeter cube, so I should change it to centimeter cube. Centimeter means 10 to the power minus 8 centimeter it will be. Okay, so this will be minus 8, so it will be 24. Yeah, so it will be 10 to the power minus 1, means 20 divided by 10, that means 2. So N is equal to 2. That means it's a unit cell with 2 atoms in it. That means it's a body-centered atom crystal. So this is the correct answer, C option. So yeah, just be careful with the conversion of units. Be careful about that. Okay. Next question. If the lattice parameter for a FCC crystal is 2.14 angstrom. Find out the value of atomic radius. Okay, we have been given lattice parameter, we have to find out the atomic radius. Now for FCC, again we know FCC, all the phase atoms on phase diagonal touch each other, and the phase diagonal length is root 2a is equal to 4r. A we know it is 2.14 angstrom. So R I can find out, multiplying this I'll get 2.14 times root 2 divided by 4. So R will be 0.7566 angstrom. Here the closest matching answer is this, 0.76 angstrom. This was pretty straightforward. Next question is about NaCl. NaCl crystal has a cubic structure and its density is given, which is 2.17 gram per centimeter cube. Be careful, here the answer is in gram per centimeter cube. Find out the distance between two adjacent atoms of the same kind. I think we need to find out A here. Atomic weight is given. There are 4 formula units contained within the unit cell, means one unit cell has 4 NaCl atoms. That means it seems it's like FCC, but anyway. So one unit cell has 4 formula units and 4 NaCl. Now we know the formula of density for unit cell. It is number of molecules multiplied by atomic weight divided by Avogadro number and volume. Density we already know. We need to find out volume actually, so that with volume I can find out the A parameter, right? So volume we need to find out. So it will become density times Avogadro number divided by number of molecules and atomic weight, and this will be A cube. Okay, so density is 2.17 gram per cc, and Avogadro number 6.023 times 10 to the power 23 divided by, here 4 formula unit are there within one unit cell, so 4, and atomic weight 23 plus 35.45, 23 plus 35.45 gram per mole, and 1 mole has Avogadro number of atoms in it, so this is taken care of. So when we'll do this multiplication and division, 6.023 multiplied by 2.17 divided by 4 divided by 23 plus 35.45 will get 0.055, and I'm getting 0.0559 multiplied with 10 to the power 23. Then I'll take, this is in gram, this is in centimeter, this is in, okay, fine. So when, oh, there's no space. Okay, so A cube was that, so A will be 1/3 of volume. So I'll get 5.63 10 to the power minus 10 in minus 8 centimeter, and in angstrom this will be 5.63, right, because this is 10 to the power 23. If we take here, it will become 10 to the power 24, and 1/3 of it will be 8. So this is how we get this, and this will be angstrom, 5.63 angstrom. So the correct answer will be option A. Okay. Next question. In a tetragonal crystal, okay, so this is tetragonal, that means angles are all equal and 90 degree, but the parameters are different. A is equal to B, given 2.42 angstrom, and not equal to C, and C is 1.74 angstrom. This is what a tetragonal crystal is. Find out interplanar spacing between 101 planes. Okay, so recalling the formula, for cubic we used to get the direct formula because A equal to B equal to C, but here it's not cubic, it's tetragonal, so our formula that we'll use will be this one: h by A square plus k by B square plus L by C square. All this is under the root. Okay, now HKL plane is 101, means D101. Here h is 1, so 1 by A square plus k is 0, L is 1, so 1 by C square minus half, right? Because it's 1 by root 2. A is given, C is given. When we'll put the value, it will be 1 over 2.42 angstrom square, and this will be 1 over 1.74 angstrom square. So the answer we'll get is 1 over 2.42 square plus 0 plus 1 by 1.74 angstrom square and whole minus 1 by 2. When we'll do this, we'll get the answer as 1.41 angstrom. Okay, A is the correct answer. Next question. A solid with FCC structure has a lattice constant 4 angstrom, and this is FCC structure. Each atom in the solid has a mass of 4. Each atom mass is 4 times 10 to the power minus 26 kg. Calculate number of conduction electrons in 1 meter cube volume of solid if each of the atom of solid contributes 2 electrons. So what they are saying is that each atom, that one atom gives 2 electrons. Each of the atom contributes 2 electrons. Here we have to calculate how many electrons are there in 1 meter cube volume of solid, and mass of solid is given. Okay, so we'll find out when solid is FCC structure, that means there are 4. Since it's FCC, that means in 1 unit cell we have 4 atoms, right? 1 total contribution from corner atoms, and 6 faces will contribute and give 3 atoms. So total 4 atoms because it's FCC. Okay, now volume of unit cell will be A cube, means 64 angstrom cube, and so number of atoms per unit volume. Atoms per unit volume will be, we have 4 atoms and volume is 64, and if I change it into, because the answer is in kg, so angstrom, when I change it into meter, it will be 10 to the power minus 30, right? Because 1 angstrom is 10 to the power minus 10 meter cube, and all these units are in SI units. So this, okay, the atoms per unit volume is 1 over 16, means 6.25, and this will be 10 to the power 28 atoms per meter cube. So each atom, we have been told, contributes 2 electrons. So 1 meter cube because atoms per volume is this. That means in 1 meter cube, we have 6.25 times 10 to the power 28 atoms. And each atom is contribute 2 electrons. That means 6.25 times 10 to the power 28 atoms will contribute 6.25 into 10 to the power 28 into 2. These number of electrons we'll get. This will be 1.25 10 to the power 29 per meter cube. So 1 meter cube has this many number of atoms, and since one atom is contributing 2 electrons, so total number of electrons in this 1 meter cube will be 1.25 10 to the power 29 meter cube. This is the correct answer. I have some more questions related to XRD, so let's do them also. So they're very easy, but just to tell how we use this when we do XRD, how do we analyze those data, what do we calculate from that. So here you just keep in mind the question is based on XRD. Bragg's condition we should remember, and then the parameters we'll put and get the answer. So here the question is wavelength of X-ray is 0.071 nanometer, which diffracted by plane of salt, means NaCl, with 0.28 nanometer as the lattice constant. Lattice constant is 0.28 nanometer. Determine the glancing angle theta for second order diffraction. Assume the value of salt plane to be 110. This we have to consider 110. And given salt is rock salt, whichever salt it is, but okay, we have to go for 110. Okay, so here, we need to find out glancing angle means theta. This we need to find out. N we know, it is 2, lambda we know. We don't know D, the interplanar spacing between 110 plane. We need to find out first that, because in this equation only one unknown can be there. Right now we don't know theta, we don't know D. So first we need to find out D. Interplanar spacing between 110, because it's a cubic, so I can directly use my formula. A is equal to under root h square plus k square plus L square. This will be A is given 0.28 nanometer divided by 1 square 1. This will be 1 and this will be 0. That means in nanometer, this will be 0.28 divided by root 2 nanometer. When I substitute the value of this in this equation, I will get 2, 0.28 divided by root 2 sine the theta I need to find out is equal to n is 2, lambda is 0.071 nanometer. Sorry, 0.071. So 2 cancel. When I will multiply this, 0.28 divided by root 2 and divided by 0.071, we will get, let's see, 0.28 divided by root 2 divided by 0.071. Answer is 2.7886. Sine theta is equal to 1. Sine theta will be 1 over 2.7886 and theta will be sine inverse of this. So when I'll get theta is equal to 21 degree. Okay, this is the answer here. Glancing angle is 21 degrees. So here we use Bragg condition, but since D was unknown, so first I need to calculate D. Okay, after calculating D, I'll substitute in Bragg equation, then I can find out theta. One more question. The wavelength of first order X-ray. First order we have to deal with. X-ray are wavelength is 2.20 angstrom and theta is 27 degree 8 minute. Okay, find the distance between adjacent Miller plane. Distance between adjacent Miller plane. Okay, So our bragg condition 2d sine theta is equal to n lambda. 2d we need to find out, that is our d. Sine, now theta it is 27 degree 8 minute. So actually 1 degree has 60 minute and 1 minute has 60 second. So this is how 1 degree is divided. It's not time, this minute is not time, it's that 1 degree is further divided into 60 units that we call minute. So 1 degree is 60 minutes, means 8 minute will be 8 divided by 60 degree, means 0.133 degree. Okay, that means total this is 27.133 degree. 27 degree 8 minute means 27.133 degree is our glancing angle. When I substitute that value here, and n is 1, lambda is given 2.20 angstrom. When we do this, sorry, okay, let's do. So d will be 2.20 angstrom divided by 2 divided by sine, sorry, 133 degree. So this will be 2.20 divided by 2, that means 1.1 divided by the sine of this, sine of 27.133 is 0.456. When we divide this, we'll get 2.41 angstrom. 1.1 divided by yeah, 2.41 angstrom. So the answer here is distance between adjacent Miller plane is 2.41 angstrom. So okay, these were the we had this time. These were the things. And time is also up. If you guys don't have any question, I'll close the session. If you have more question, next time also if you feel like asking anything, you can ask. Because for understanding these, I assume you will be watching the lecture, of course. But still, if you have doubt, you can ask next time. Mainly here I was focusing on doing all these lot of problems so that it will help you in solving your assignments. Okay. So if there are no questions, I'll stop recording.